Hello student, welcome to my channel Learn Physics. Today I will be discussing the gravitation. My discussions are first of all Newton's law of gravitation, acceleration due to gravity, variation of gravity due to shape of the earth, altitude from the earth's surface and depth from the earth's surface. And we also discussing the variation of g due to rotation of earth, then gravitational intensity, gravitational potential, escape velocity, Kepler's law of planetary motion and motion of satellites. So this discussion will be very interesting for you. If this discussion is beneficial for you, please share and subscribe my channel. Okay, now let's start. Suppose two masses m1 and m2 separated by a distance smaller. The Newton's law is the force of attraction between any two particles is directed along the line joining them. The magnitude of this force is directly proportional to the product of their masses, that is F proportionate, this is the m1 into m2. And finally this force is inversely proportional to the square of the distance of separation, that is F proportionate 1 by r square, and this force is independent of medium. Now combining these two relations we get F equal to g, this is the m1 m2 divided by r square. Look at this, if mass of both the particle becomes 2 times, then force of attraction becomes 4 times. If distance of separation becomes twice the initial, keeping their mass constant, then force of attraction becomes F by 4. Okay, if both mass of two bodies and their distance of separation are increased by 2 times, then gravitational force of attraction F equal to g into 2m1 2m2 by 2r whole square, that is F. So force of attraction remains same. The term capital G is called universal gravitational constant. Now we define capital G with the help of this equation. Look at this, if r equal to 1, m1 equal to m2 equal to 1, then capital G equal to F. Therefore universal gravitational constant is the force of attraction between two unit masses separated by unit distance. Its value is G equal to 6.67 into 10 to the power minus 11 Newton meter square divided by kg square. Okay, now vector form of Newton's law of gravitation. Look at this, the force on m1 by m2 directed along this direction. Okay, so look at this, the vector form of Newton's law of gravitation is g m1 m2 divided by r square into r cap. This is the gravitational force of attraction on m1 by m2, and r cap is the unit vector directed in the direction from m1 to m2. In the same way, if f2 vector be the force of attraction on m2 by m1, then this becomes, look at this, this is the g m1 m2 by r square into minus r cap. Okay, so look at this, this is the minus g m1 m2 by r square r cap. So look at this, this is the minus F1. Okay, look at this, mass small m and capital M minus small m are kept at a separation of smaller. We have to calculate small m by capital M such that the gravitational force is maximum. Now look at this, suppose this is the mass m and this is the capital M minus small m and distance of separation is r. So gravitational force of attraction F equals to g, product of this mass and this mass. So this is the gm capital M minus small m whole divided by r square. So look at this, this is the g capital M small m minus m square divided by r square. For maximum force of attraction, df by dm is equal to 0. So look at this here, df by dm, this equals to g. Now differentiation of this with respect to small m, so this is the capital M into 1 and this is the minus 2m whole divided by r square. For maximum force, df by dm equal to 0. So look at this, from this condition we can write g by r square, this is the capital M minus 2m, this equals to 0, therefore small m equal to capital M by 2. So here small m by capital M, this is the half. So look at this, the force of attraction becomes maximum when mass of two parts are equal. As small m equal to m by 2, so this is the capital M by 2 and this also capital M by 2. So if a mass is divided into two parts such that the force of attraction becomes maximum, so mass should be identical. Okay, now Ncert 8.12, the orbital radius of Earth around the Sun is 1.5 into 10 to the power 11 meter. A rocket is fired from the Earth's surface. Find position of the rocket where gravitational force of attraction due to Earth and due to Sun becomes equal and opposite. Okay, now first of all, this distance is x from the r. Suppose this distance is x from the earth's surface, where net gravitational force on the rocket is 0. Therefore this distance obviously becomes r minus x. So look at this. Now what is this force? This is the g, me, small m is the mass of the rocket and this is the x square. Okay, g, mass of the earth, mass of the body, that is rocket, by distance square. Now look at this, fs, this is the g, this is the mass of the sun, this is the mass of the rocket divided by r minus x whole square. Okay, now look at this, this cancel out. Therefore r minus x by x whole square, this equal to, this is the ms by me. Now what is the ms? ms is the 2 into 10 to the power 30 kg. So this is the 2 into 10 to the power 30 divided by, this is the 6 into 10 to the power 24. Okay, so r minus x divided by x, this is the root under of 10 to the power 6 by 3. So this is the 10 to the power 3 divided by 1.7. Okay, now multiplying this. So look at this, this is the 1.7 r minus 1.7x equals to, this is the 1000x. So this is the 1.7 r equal to 1001.7x. So x equals to, look at this, 1.7 divided by 1.001.7 into, what is the r? R is the 1.5. So this is the 1.5 into 10 to the power 11. So look at this, this is the 1.7 into 1.5 into 10 to the power 8. Look at this, this is almost 10 to the power 3. So 10 to the power 3, here 10 to the power 11, so 10 to the power 8. Distance of the rocket from the earth, this is the 2.6 into 10 to the power 8 meter. Okay, next. Now acceleration due to gravity. When a body falls under gravity, its rate of change of velocity with respect to time is called acceleration due to gravity. On Earth's surface, g equal to 9.8 meter per second square, and its expression g equal to capital G, capital M divided by r square. Now we have to establish this relation. Look at this, suppose this is the earth. A mass small m is on the earth's surface. Mass of the earth is capital M and its radius is capital R. Okay, this is the capital R. Now the force of attraction on small m towards the center of the earth F equal to, this is the G capital M small m by r square. This is the gravitational force of attraction. Okay, if acceleration due to gravity is small g, then this F is equal to mass into acceleration due to gravity according to Newton's second law of motion. So look at this, here mg equal to, this is the g capital M small m divided by r square. Now this and this cancel out, so here g equal to capital Gm by r square. Okay, so g directly proportional to the mass of the earth and g inversely proportional to the distance of earth's surface from its center. Now look at this, the polar radius is less than the equatorial radius. Look at this, this is the polar radius and this is the, look at this, from this to this is the equatorial radius. So polar radius is less than the equatorial radius. So here g at pole, as its radius is less, greater than g at equator, because g is inversely proportional to the square of that distance. Okay, look at this, if earth sink such that its radius becomes decreased by 1% or 2%, how g changes? Look at this, for small variation of r, delta g by g, this equal to minus 2 delta r by r. Okay, that is, if radius of earth shrink by 1%, then acceleration due to gravity, look at this, this is the minus 2 and shrink by 1%, that is radius decreased by 1%. So look at this, this is the minus 1%, so this is the 2%. If radius of earth shrink by 1%, then acceleration due to gravity increased by 2%. In the same way, if the acceleration due to, if the radius of earth shrink by 2%, then acceleration due to gravity increased by 4%. Okay, understood? Next, again we have to establish the relation between small g and mean density of earth. If rho be the mean density of earth, then its mass m equal to volume into density. Look at this, this is the volume of the earth and rho is mean density. Now if we put the value of m in this equation, we get g equal to g, this is the 4/3 pi r cube into rho whole divided by r square. So look at this, this is the 4/3 pi r, 0 is the expression of g in terms of mean density of earth. Okay, look at this, for constant mean density g directly proportional to r. So two planets having same mean density, the acceleration due to gravity on this planet is directly proportional to their radius. Okay, understood? Next, now we have to establish the relation between acceleration due to gravity with altitude from the earth's surface. So we have to establish this relation: g dash is equal to g r square divided by r plus h whole square equal to g into 1 minus 2h by r when h very less than r. Okay, that is 1 kilometer, 2 kilometer, 20 kilometer, etc. Okay, now look at this. We know the acceleration due to gravity on earth's surface, this is the g equal to gm by r square. Okay, this is equation number 1. Okay, now the acceleration due to gravity at an altitude h, this is the g dash. Here force of attraction on small m divided by mass of it. What is the force of attraction on m due to earth? Look at this. This is the capital G, capital M, small m divided by r plus h whole square. Look at this. This is the h and r is the radius. So distance of small m from the center of the earth is r plus h. So look at this. This is the m. Now this and this cancel out. Therefore g dash equals to, this is the gm divided by r plus h. This is the whole square. Now this is equation 2. So here g dash by g, this is the r divided by r plus h whole square. Okay. To establish this relation, we have to utilize the binomial theorem. Now, if we divide numerator and denominator by r square, we get 1 divided by 1 plus h by r. This is the whole square. So, this is the 1 plus h by r to the power minus 2. Look at this. If h very less than r, so h by r is very less than 1. In this condition, g dash by g, this equals to 1 minus 2h by r. So look at this. Here g dash equal to g into 1 minus 2h by r. Okay, understood? If we draw a graph of g with h, then the graph becomes, look at this. This is the h and this is the g. So graph so g decreases with altitude and becomes 0 at infinity. Okay, understood? Next, now Ncert numerical 8.15. The weight of a body on Earth's surface is 63 Newton. We have to calculate the weight of the body at an altitude h equal to r by 2, where capital R is the radius of the earth. Okay, we know acceleration due to gravity g dash, this equals to g into r square divided by r plus h whole square. Now multiplying this equation by m. So look at this. This is the m, this also m. Now here mg is equal to 63 into r square divided by r plus, what is the h? H is the r by 2. So this is the r by 2 whole square. Okay. Now mg dash, this is the mg, means 63 into r square divided by, now look at this. This is the r plus r by 2. So this is the 3r by 2 whole square. Okay. So this is the 63 into, this is the r square divided by 9r square divided by 4. This and this cancel out. So this is the 63 into 4 by 9, that is this and this 7. So this is the 28. So weight of the body at an altitude h equal to r by 2 is 28 Newton. Okay, understood? Next, now we have to establish the relation of g with depth. That is g dash equals to g into 1 minus x by r, where x is the depth from the earth's surface and g is the acceleration due to gravity. suppose an object of mass m is on the earth surface. If rho be the mean density of the earth, then its mass capital M is the 4/3 pi capital R cube into rho. The gravitational force of attraction on M on its surface is F equal to, this is the G capital M small m divided by R square. So here G equal to F by M, this equal to G capital M by R square. Now if we put the value of M, we get, this is the G, this is the 4/3 pi capital R cube rho by R square. So look at this, G equal to, this is the 4/3 pi R into 0 is the acceleration due to gravity on the earth's surface. Okay, now we have to calculate, now we have to find an expression of G with depth. Suppose, look at this, suppose the mass M is at a depth x from the earth's surface. Now this mass will be the surface of a sphere of radius r minus x. So look at this, here acceleration due to gravity G dash r should be replaced by r minus x. So this is the 4/3 pi, this is the r minus x into G into rho. This is equation 2. Okay, now if we divide equation 2 by 1, so G dash by G, this equals to r minus x by r. So this is the 1 minus x by r. So here G dash equals to G into 1 minus x by r. Okay, now at the center of the earth, the depth is r. So look at this, here G dash equal to G into 1 minus r by r. So this is the 0. So at the center of the earth, the acceleration due to gravity becomes 0. Understood? Now if we draw a graph between G and distance from the center of the earth, the graph becomes straight line within the earth. Look at this, this is the G, this is the graph between G and distance from the earth. This is the R and this is the G. Okay, and this is the R equal to 1. Outside the earth, this is the G proportionate 1 by R square. So outside the earth, G inversely proportional to square of the distance from the center of the earth. Okay, now Ncert 8.16. The weight of a body on the earth's surface is 250 Newton. We have to calculate the weight at a depth of r by 2. The relation between G dash and G is G dash equals to G into 1 minus x by r. So if we multiply M, this equation we can get, look at this, this is the mg dash equal to mg into 1 minus x by r. Look at this, here mg given, this is the 250 Newton. So this is the 250, 1 minus, this is the r by 2 by r. So look at this, this is the 250, r cancel out, so this is a 1 minus half. So look at this, this is the 250 into half, so this is the 125 Newton. Okay, so weight of the body at a depth r by 2 is the 125 Newton. Okay, now variation of G due to rotation of earth. Look at this, the earth rotates about its own axis, and due to this rotation, every particle on the earth's surface experiences an outward centrifugal force except at the particle at pole. So look at this, at the equator, this centrifugal force, this is the m omega square r. So here weight of the body mg along this direction. So at equator the weight becomes mg dash equal to mg minus m omega square r. Therefore g dash equal to g minus omega square r is the expression of acceleration due to gravity due to rotation of Earth. Now we have to establish a relation of g at any point. Suppose a particle is at a latitude phi. So radius of the circular path described by the particle, this is the smaller, okay. So centrifugal force experienced by this particle, this is the m omega square r. Now if this angle phi, then this angle also phi, and this is the capital R. So here look at this, smaller by capital R, this is the cos phi. So smaller equal to capital R cos phi, okay, no problem. Now this is the weight of the body acting towards the center. Now the component of m, now component of this force away from the weight of the body, this is the m omega square smaller cos phi. So look at this, at any point the weight of a body mg dash, this is the mg minus m omega square smaller cos phi. Now smaller cos phi equal to capital R cos phi. So this is the mg minus m omega square capital R cos square phi. So g dash is equal to g minus omega square r cos square phi is the expression of g due to rotation of Earth. Look at this, if angular velocity of Earth rotation increases, then acceleration due to gravity decreases. If Earth stop rotation, then negative term vanishes, so g increases, okay. Now a numerical, find angular velocity of Earth rotation if weight of a body on the equator becomes 0 and half of real weight. Look at this, suppose this is the Earth. Here mg directed along this direction and centrifugal force m omega square are directed this direction. So look at this, here mg dash equal to mg minus m omega square r. Now here weight 0, that is mg dash 0. So this is the 0 equal to mg minus m omega square r. So look at this, here m omega square r, this is the mg. Now this and this cancel out. So look at this, omega equal to, look at this, this is the g by r. Now g is the 10 and r is the 6400 into 10 to the power 3. So look at this, this is the 1 by 800 radian per second. Now what will be the duration of a day? Look at this, t equal to, this is the 2 pi by omega. So this is the 2 pi divided by 1 by 800. So this is the 1600 pi. That is, so 1600 pi, this is the second. Therefore this is the 1.4 hour. Okay, understood? Now next problem. The weight of the body becomes half of the real weight. So look at this, here mg dash becomes, look at this, this is the half of mg. Okay, understood? Now half of mg equal to mg minus m omega square r. Look at this, here m omega square r equal to mg minus half mg. So this is the half mg. Here omega square equal to g by 2r. Therefore omega equal to, look at this, omega equals to root under g by 2r. So omega equals to, look at this, 1 by root 2 into, look at this, g by r. So this is the 1 by root 2 into 800. This is the radian per second. What will be the period? As root under g by r equals to 1 by 800. So omega equal to 1 by root 2 into 1 by 800. So this is the 1 by 800 root 2. Okay, is the angular velocity of Earth rotation. Okay, and unit of it, this is the radian per second. So duration of day t dash, this is the 2 pi by omega. So look at this, this is the 2 pi by 1 by 800 into root 2. This is the root 2 into 2 pi into 800 second. Therefore this is the root 2 into 1.4 hour. So look at this, this is the 2 hour. Okay, so duration of day becomes 2 hour. Okay, next, now gravitational intensity. Gravitational intensity is the force experienced by a unit mass of a body in a gravitational field. Look at this, suppose this is a body of mass capital M. We have to calculate gravitational intensity at the point P due to this mass. Suppose this distance r, so we place a unit mass here. So force experienced by this unit mass due to capital M is the gravitational intensity. So look at this, the gravitational intensity E equal to capital G, mass of this into mass of this. So m into 1 divided by r square. So E equal to, this is the gm by r square, is the expression of gravitational intensity. Now its unit is Newton per kg or meter per second square. That is acceleration due to gravity. Okay, outside the solid sphere E equal to gm by r square. Now inside it, this is the E equal to, this is the g capital M small m by r cube, where capital R is the radius of it. If we plot a graph between intensity and distance r, this graph is just like acceleration due to gravity and distance graph. Okay, look at this. This is the E proportionate r and this is the E proportionate 1 by r square. Look at this, in terms of mean density of earth, we establish this relation. Look at this, g mass is the 4/3 pi capital R cube rho into small r by r cube. Okay, so now look at this, this is the 4/3 pi g rho into small r. Look at this, here E proportionate r. Understood? Next, in case of a spherical shell, there is no mass inside it, so E inside the spherical shell is 0, and outside the spherical shell E equal to, this is the gm by r square. So graph between E and R just become, look at this, this is the small r equal to capital R, and the graph starts from here because in this position the E equal to 0. Okay, understood? Now a numerical. Look at these two masses m and 9m are at a distance smaller. Look at these two masses m and 9m are at a distance of r. Now we have to find a point where gravitational intensity is 0. Suppose this is the point where gravitational intensity is 0. Now gravitational intensity at this point due to this mass directed along this direction. Now gravitational intensity due to this mass is directed along this direction. Now if this is the E1 and this is the E2, if E1 equal to E2, then gravitational intensity at this point becomes 0. So this is the E1 equal to E2. Suppose this distance is x. Okay, so this distance, look at this, this distance must be r minus x. So here E1 equal to g m divided by distance square, and E2 equals to g into mass, this is the 9m divided by r minus x whole square. Now this cancel out, so this is the 1 by x whole square, this equals to 3 by r minus x whole square. Okay, so look at this, this is the 1 by x equal to 3 by r minus x. So this is the 3x equal to r minus x. This is the 4x equal to r. Therefore x equals to r by 4. Therefore at a distance of r by 4 from small mass, the gravitational intensity becomes 0. Now potential. Suppose this is a mass m this is the point P. P is at a distance r from the mass m. So potential at the point P is the amount of work done to bring an isolated unit mass from infinity to a point P in the gravitational field. It does not depend on path, it depends on initial state to final state. So it is a state function. Okay. Now derivation. Intensity at the point P due to mass capital M is E equal to, this is the G capital M by R square, and it is directed towards the mass capital M. Now amount of work done to displace a unit mass through the distance dr towards capital M is E into dr. So gravitational potential at the point P is V equal to, look at this is the integration of this work done. So this is the E into dr, and what is the limit of integration? As potential is the work done to bring the unit mass from infinity to the point P, that is R. So the limit of integration is infinity to R. Now put these values. Okay, very simple. So look at this is the infinity R, this is the Gm by R square dr. Okay, now look at this G capital M constant. So look at this here, this is the G capital M, and here R to the power minus 2 dr, integration infinity to R. Now there is a formula of integration x to the power n dx. So this is the x to the power n plus 1 divided by n plus 1. Okay, understood? So here n equals to minus 2. So look at this becomes Gm, and this is the R to the power minus 2 plus 1 divided by minus 2 plus 1. Limit of integration infinity to R. Okay, no problem. Look at this, minus 2 plus 1, that is minus 1. Now look at this, so this is the minus Gm, and look at this here, R to the power minus 1 plus 1, that is R to the power minus 1. R to the power minus 1 means 1 by R. So look at this becomes 1 by R minus 1 by infinity. So expression of potential V equal to, look at this is the minus Gm by R. Okay, what is its units? Its unit is, look at this, work done by mass, that is joule per kg. Okay, understood? Now I will be solving two numerical based on potential. Okay, now the numerical. Infinite number of masses m are present at x equals to 1, x equals to 2, x equals to 4, x equals to 8 ... We have to calculate potential at the origin. Now look at this. Suppose this is the x-axis, here x, and this is the origin O. Okay, now here mass m is placed here 1, here mass m is placed this point, here mass placed this point, and here mass m placed this point, and so on. So look at this, the potential at O, this is, look at this, the potential at O, VO, this equals to potential due to this mass. So this is the minus Gm by 1. Now potential due to this mass at O, it is the minus Gm divided by 2. Okay, now potential due to this mass is also minus Gm divided by 4, and potential due to this mass, this is the minus Gm divided by 8 plus ... Okay, no problem. Now look at this is the minus Gm, this is the 1 by 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus ... Okay, no problem. Therefore this equals to minus Gm, this is the infinite GP series, and here common ratio is the half. Look at this, 1 half, 1 by 4, 1 by 8. Common ratio is the half. Now for infinite GP series, the addition is A divided by 1 minus R. A is the first term, so this is the A. And R is the, look at this by this by this, so this is the half. So for infinite GP series, this is the 1 divided by 1 minus R. R means half. Okay, understood this formula? Okay, now this becomes, look at this, minus GM divided by, this is the half, so this is the minus 2 GM is the expression of potential due to infinite masses placed at x equals to 1, x equals to 2, x equals to 4, x equals to 8, dot 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 dot. Okay, understood? Please share this video. Okay, look at this. Mass m and 4m are placed at a distance smaller. We have to calculate the potential at a point where gravitational intensity is 0. Now look at this, we know the expression of gravitational potential V equal to minus Gm by R, and expression of intensity, this is the minus, and expression of intensity, this is the Gm by R square. This is the scalar quantity and this is the vector quantity. The direction of gravitational intensity is directed towards the mass m. Okay, now look at this is the figure. Here mass m and here mass 4m. They are at the separation r, no problem. Now first of all, we have to calculate a point where gravitational intensity is 0. Look at this, suppose this is the point where gravitational intensity is equal to 0. Now this distance is the x. So gravitational intensity at this point due to this mass is directed along this direction. Suppose this is the E1, and gravitational intensity at this point due to this mass is directed along this direction. Suppose this is the E2. If E1 equal to E2, so gravitational intensity at this point becomes 0. Understood? So look at this. First of all, E1 equal to E2. We take this distance x. So this distance obviously r minus x. Okay, no problem. Total distance r. This is the x. So this is the r minus x. No problem. So look at this. E1 is the Gm divided by distance square. Look at this. This is the distance. So this is x square. Now E2, G is the mass 4m divided by this distance square. So this is the r minus x whole square. Now we have to calculate x from this relation. Look at this. This cancel out. Okay. Look at this. So this is the 1 by x square equal to 4 divided by r minus x whole square. Okay, understood? Next, this is the 1 by x whole square equal to 2 by r minus x whole square. So look at this. This is the 1 by x equal to 2 by r minus x. No problem. Now look at this. This is the 2x equal to r minus x. So look at this, 2x and x. This is the 3x equal to r. Therefore x equals to r by 3. Okay, understood? Now we have to calculate the potential at this point. Okay, so potential at this point, V equal to minus Gm by x plus G4m divided by r minus x. Look at this. Potential is the G into m by distance. Look at this. This distance is x and this distance is r minus x. Okay. Now put the value of x here. Sorry, this is the minus side. Okay. Now look at this. This is the minus Gm. This is the 1 by x means 1 by r by 3. Plus, look at this, is the 4 divided by r minus r by 3. Look at this, r minus r by 3, that is 2r by 3. So look at this, this is the minus Gm divided by 3 by r plus, look at this, this is the 6 by r. Okay, so this is the minus 9 gm by r is the expression of potential where gravitational intensity is 0. Okay, please share this video. Okay, I hope you understand the potential and related numerical. Now I will be discussing potential energy. Now first of all definition and then expression. The potential energy is the amount of work done to bring an isolated mass from infinity to a point in the gravitational field. It is also a scalar quantity and a state function. We have to find the expression of potential energy. Now potential energy is the work done for a mass and potential is the work done for a unit mass. So potential energy is the potential into mass of the body. Therefore U equal to, this is the minus G capital M small m divided by R is the expression of potential energy. Okay, now work done. Work done is equal to potential energy at the final position minus potential energy at the initial position. So look at this work done delta W, this is the U2 minus U1. Okay, now look at this, this is the minus G capital M small m by R2 minus G capital M small m divided by R1. Okay, so this is the G capital M small m, this is the 1 by R1 minus this is the 1 by R2. Okay, this is the expression for work done. Now I will be solving two numerical based on potential energy. Okay, now look at this. Four masses M, 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 M are placed at the vertices of a square. We have to calculate potential energy of the system. Okay, now the expression of potential energy, this is the minus G capital M small m divided by R, where R is the separation between the two mass capital M small m. Okay, where R is the separation between the two masses capital M and small m. Now look at this, the potential energy between this mass and this mass, this is the, look at this, this is the minus G M into M divided by A. Okay, now potential energy between this mass and this mass, look at this, this distance is the root 2 into A. So this is the minus G M into M whole divided by, this is the root 2 into A. Now potential energy between this mass and this mass, so this is the minus G M into M divided by A. So we calculate potential energy between this and this. Okay, now we have to calculate potential energy between this and this. Okay, so look at this, the potential energy between this mass and this mass, this is the minus Gm into M divided by A. Now potential energy between this mass and this mass, this is the minus Gmm divided by this distance is the root 2a, so this is the root 2 into a. Now finally we have to calculate potential energy between this mass and this mass, so this is the minus Gmm divided by a. Okay, now again, first of all we have to calculate potential energy between this, then between this and this, and between this and this, and finally between this and this. Okay, so there are 6 terms occur. So look at this are identical term, so this is the minus 4Gm square by A. Look at this and this are identical term, so this is the minus 2Gm square by root 2a. So look at this this is the negative sign of 4. Look at this, this is the root 2. So 4 plus root 2 into gm square by A is the potential energy of this system. Okay, understood? Next. Now another numerical relating to potential. A mass small m is raised from the earth's surface to an altitude h equal to r, radius of the earth. We have to calculate work done to this. Now the formula for this numerical work done is equal to, this is the U2 minus U1, that is potential energy at the final position minus potential energy at the initial position. You know the expression of potential energy U equal to, this is the G m1 m2 divided by R, okay, and with negative side. Understood? Suppose this is the surface of the earth. Mass m is raised from surface of the earth to an altitude h equal to r. We have to calculate work done. Now this is the initial position. So potential at this point is U1, and this is the final position. The potential at this point is U2. Radius of the earth is capital R. Okay. Now distance. Now the distance of this point from the center of the earth is capital R. So this is the R1. So what is the initial potential energy? This is the minus G. This is the mass of the earth, mass of the body divided by distance of the body from the center of the earth. Okay. Understood? Now potential energy at this point. Look at this. This is the R and this is also R because H equal to R. So distance of this mass from the center of the earth is R plus R, that is 2R. So look at this, U2 becomes minus G capital M small m divided by 2R. Understood? Now the work done. Work done is the potential energy at the final position minus potential energy at the initial position. Understood? So look at this, work done delta W, this is the U2 minus U1. So look at this, this is the minus GMM by 2R minus GMM by R. Okay, understood? Now look at this, this is the GMM by R, this is the 1 minus half. Okay, understood? So this is the G capital M small m divided by 2R. Now we know G equal to Gm divided by R square, acceleration due to gravity on the earth surface. So G capital M is equal to GR square. So look at this, the work done delta W, this is the GR square M divided by 2R. So this is the half mgr is the work done to raise the mass from earth's surface to an altitude h equal to r. Understood? Please like this video. Okay. Now there is an important relation which help us to solve the numerical relating to velocity of the body. This relation is the conservation of energy. Suppose this is the earth surface, a body projected from the earth surface with velocity v1. When it reaches the height h, its velocity becomes v2. Now we have to express the relation between height h, v1 and v2. Capital R be the radius of the earth. This relation will immensely help you to solve the numerical relating to velocity of a body in the gravitational field. So at this point, the potential energy U1 and kinetic energy is, this is the K1, and at this point potential energy, this is the U2, and kinetic energy the K2. Look at this, as this is the surface of earth, so distance of this point from the center of the earth is capital R. So look at this, the potential energy at the surface of earth, this is the G mm by capital R, where m is the mass of the projected body. Now what is the kinetic energy? Look at this, velocity v1, so this is the half m v1 square. Now potential energy at this point, look at this, the distance of this point from the center of the earth, this is the r and this is the h, so this is the r plus h. Understood? So potential energy at this point, this is the G capital M divided by this is the R plus H, and kinetic energy, what is the, this is the half m v2 square is the kinetic energy. Now for maximum value of H, v2 becomes 0. When H becomes maximum, okay, then v2 becomes 0. Okay, now I will be solving two numerical relating to this formula. Okay, now the numerical, a body is projected from the earth's surface. Find the velocity of projection if it reaches h equal to 4r. That is, the body reaches from earth's surface to an altitude h equal to 4r. Now what is the formula? Formula is the conservation of mechanical energy, U1 plus Q1 equal to, this is the U2 plus K2. Okay, now we have to draw a figure. Look at this, this is the earth's surface. The body is projected with velocity v and it reaches the height, this is the h equal to 4r. As it is the maximum height, so v2 becomes 0. Okay, so v2 becomes 0. Now look at this, what is the u1 on the earth's surface? Look at this, u1 is the minus g capital M small m divided by distance of this point from the center, that is the radius. Now what is the distance of this point from the center? Look at this, this is the 4r and this is the r, so this is the 5r. So look at this, u2 becomes minus g capital M small m, this is the r plus 4r. So look at this, this is the minus g capital M small m by 5r. Okay, understood? Now what is the kinetic energy? Kinetic energy Q1, this is the half mv square. Okay, v to be obtained. Now what is the final kinetic energy? As this is the maximum height, so v2 0, therefore kinetic energy K2 also 0. So this is the 0. So look at this, this is the u1 plus Q1 equal to u2 plus K2. Okay, now look at this, u1, this is the minus g capital M small m by r plus, look at this is the half mv square. Look at this, this is the minus g capital M small m divided by 5r plus 0. Okay, understood? So look at this, this is the half mv square, this equal to g capital M small m by r minus g capital M small m divided by 5r. Now look at this, g capital M small m divided by r, this is the 1 minus 1 by 5. Okay, so look at this, v square equal to, this is the 2 gm by r, this is the 4 by 5. So look at this, gm is equal to gr square. Look at this, we know g equal to gm by r square, so gm equal to gr square. So look at this, this is the 8 gr square by 5r. So look at this, this is the 1.6 gr. Okay, understood? Next, so velocity v equal to root under 1.6 g into r. Look at this, this is the 1.6 into g is the 10 and r is the 6400 kilometer. It should be converted into meter, so we multiply by 1000. Okay, now look at this, this is the 8000, this is the root over 1.6 into 8000 meter per second. Okay, now root over 1.6 means 1.26 into 8 kilometer per second. So velocity of projection almost 10 kilometer per second. Okay, now look at this. Two masses 10 kg and 20 kg are at stationary at a separation of 1 meter. Due to mutual gravitational force of attraction, they attracted towards each other. When they reaches at the separation of 0.5 meter, we have to calculate their velocity. Here only mutual gravitational force acting between them. So this is the internal forces of attraction repulsion in the system of 10 kg and 20 kg. So conservation of linear momentum is obeyed. So look at this. This is the 10 into V1. This is 20 into V2. So V1 is equal to 2V2 is the relation of their velocities. Okay. Now we have to calculate the velocity V1 and V2 in terms of capital G. Look at this. So first of all, this is the U1 plus K1 equal to U2 plus K2. Look at this. The potential energy between these two bodies is the G capital M small m by R. So look at this. This is the minus G into 10 into 20 divided by distance of separation, that is the 1 meter. Now what is the kinetic energy? Look at this, they are stationary. So kinetic energy 0. Now look at this U2, this is the minus G, this is the 10 into 20, and look at this 0.5 meter is their distance of separation. So this is the 0.5. Now kinetic energy, look at this. This is the half into 10 into V1 square plus half into 20 into V2 square. Half into 20 into this is the V2 square. Okay. This is the minus 200 G. This equal to this is the minus 400 G plus this is the 5 V1 square plus 10 V2 square. Okay. Now this is the this side. So this is the 400 capital G minus 200 capital G. This equals to 5. Look at this, V1 equals to 2V2. So this is the 2V2 square plus 10 V2 square. Look at this. This is the 4 into 5. So this is the 20 V2 square plus 10 V2 square. Okay. This is the 200 capital G. So this is the 30 V2 square. Therefore V2 square equals to 200 G divided by 30. Look at this. This and this cancel out. Okay. Therefore V2 equal to root under of 20 by 3 into 6.67 into 10 to the power minus 11. Okay. Now relation between gravitational potential and gravitational intensity. We know the gravitational intensity is the negative gradient of potential, that is E equal to this is the minus dV by dr. Okay. So from this relation we can express in vector form. So E vector is equal to Ex I cap plus Uy j cap plus Ez k cap. Now look at this Ex, that means del V by del X I cap minus del V by del Y j cap minus del V by del Z k cap. Okay. Now we can also express the dV in terms of E. So E equal to minus E into dr. Now if we integrate this, suppose this is the VA and this is the VB and this is the RA and this is the RB. Okay. So we can get, look at this, this is the VB minus VA, this equal to minus integration of E into dr. This is the RA and this is the RB. Okay. Understood? Next, will potential be 0 if intensity 0? Look at this, if intensity 0, so this is 0. So 0 equal to minus dV by dr. Therefore minus dV equal to 0. Therefore dV equal to 0. that is V constant. Therefore, when intensity 0, potential may not be 0, it is constant. Okay. Now I will be solving two numerical relating to relation between intensity and potential. Okay. Look at this. Potential V equal to 3x minus x cube. Find the points where E 0. Now we know E equal to, this is the minus dV by dx. So look at this, here minus, this is the derivation of this is the 3 into 1 minus, this is the 3x square. Okay. As E equal to 0, so this is the 0. Therefore 0 equal to 3 minus 3x square. Okay. Therefore 3x square equal to 3. So x square equal to 1. Therefore x equal to plus minus 1. So therefore at x equals to 1 and x equals to minus 1, the electric intensity is 0. Okay. Next. Now an important numerical. V equal to 3xyz. We have to calculate E at 1, 1, minus 1. Now the formula is E vector, this equal to, this is the Ex I cap plus Ey j cap plus Ez k cap. Okay. Now you know Ex equals to, this is the minus del V by del x I cap, this is the del V by del y j cap minus this is the del V by del z k cap. Okay. Now del V by del x, that means we differentiate V with respect to x. Here differentiating V with respect to y and differentiating V with respect to z. Look at this. Now del V by del x equal to del now this is the 3xyz. Look at this, here only x variable, yz constant. So if yz constant, so the differentiation of this is the 3 into 1 into y into z. Now at this point 1, 1, this becomes, look at this is the 3 into 1 into minus 1. So this is the minus 3. Now del V by del y. Here only y constant. That is, this is the del y into 3xyz. This is the only y variable. So this is the 3x into 1 into z. So this is the 3 into 1 into minus 1. So this is the minus 3. Now del V by del z. Here only z constant. So this is the 3xyz. Look at this is the 3 into x into y into 1. So this is the 3, 1 into 1. This is the 3. Okay. So this is the 3, 1 into 1 into 1. This is the 3. Okay. So look at this here, E vector. This is the, look at this, del V by del x, negative sign. This is the minus 3. So this is the 3 I cap. This is the 3 j cap. And minus 3 k cap is the expression of gravitational intensity. Now the scalar value of this E equal to root under of, this is the 3 square plus this is the 3 square plus minus 3 whole square. So this is the 3 root 3 is the gravitational intensity at the point 1, 1, minus 1. Okay. Now the escape velocity, the minimum velocity of projection of a body by which the body overcomes the gravitational pull of Earth or a planet. It does not depend on mass of the projected body, direction of projection and place where it is projected. On Earth's surface, the escape velocity V equals to, this is the root under 2 gm by r, this equal to root over 2 gr, this equal to root over r into 8 pi g rho divided by 3 is equal to 11.2 kilometer per second. Okay. Now we derive the expression of escape velocity. The derivation of escape velocity is obtained from the conservation of mechanical energy. Suppose on the Earth's surface the escape velocity is v. So look at this here, kinetic energy, this is the half m v e square. Okay. What is the potential energy on the surface of the Earth? Look at this. This is the k equal, the potential energy U equal to, look at this, this is the minus g, mass of the Earth, mass of the body, divided by distance of the surface from the center of the Earth. This is the capital R. Now what is the potential energy at infinity? 0. Kinetic energy at infinity, this also 0. So look at this, this is the half mv square mechanical energy at the surface of the Earth. This is the minus gmm by r. This equal to kinetic energy at infinity 0, potential infinity also 0. So look at this, this is the half mve square, this is the g capital M small m divided by r. So ve equal to, look at this is the 2gm by r, is the expression of escape velocity. Now we know g equal to, this is the gm divided by r square. Okay. So gm equal to gr square. So this expression can be written as, look at this, 2gr square divided by r. So this is finally get 2gr. Now we know mass of the Earth m equals to 4/3 pi r cube rho. So look at this, this is the 2g 4/3 pi r cube rho divided by r. So this is the r into root over 8 pi g rho divided by 3. Okay. So there are three expressions of escape velocity. This is the root over 2gm by r, this is the 2gr, and in terms of mean density, this is the r into root under 8 pi 0 by 3. Okay, understood? Now we solve some numerical relating to escape velocity. Good. Now look at this. The Earth is compressed in such a way that its radius decreased by 2%. We have to calculate the variation of escape velocity. So look at this here, delta r by r, this equal to minus 2%, because decreased means this is the negative. Okay. Now we have to calculate the variation of capital. Now we have to calculate the variation of escape velocity, that is delta ve by v. This is the question mark. Now the expression of escape velocity, look at this, this is the 2gm divided by r. Okay. Now look at this here, 2 capital G capital M constant. So look at this, we can write v equals to k, this is the r to the power minus r. So look at this, this is the delta v by v, this equal to minus half delta r by r. Look at this here, delta r by r is the minus 2%. So look at this, this is the minus half into minus 2%. Therefore, this is the 1%. So escape velocity will be increased by 1%. Okay. Look at this, mass m1 and m2 are separated by the distance d. A small mass m is projected at the midpoint between the line joining the two masses with velocity v. Now we have to calculate the v such that it escapes from the gravitational pull of m1 and m2. So now we apply the conservation of mechanical energy. Look at this. So this is the u1 plus k1, this is the u2 plus k2. Now look at this, the potential energy at infinity 0. The kinetic energy at infinity also 0. So look at this potential energy. This is the minus g m1 m divided by this distance is the d by 2. So this is the d by 2. Now potential energy due to this mass, this is the minus g capital M2 m divided by d by 2 plus half mv square kinetic energy. This equals to 0 plus 0, that is 0. Okay, so look at this. This is the minus g m1 m plus, so look at this. This is the half mv square. This equals to this is the 2g small m by d into m1 plus m2. Okay, now look at this and this cancel out, so v equals to root under of 2g, this is the m1 plus m2 divided by d into 2. Okay, so this is the 2 into root under of g, this is the m1 plus m2 into d is the expression of escape velocity of mass small m. Okay, understood? Now a numerical relating to escape velocity. A person can jump 1.5 meter on Earth's surface. The mean density of a planet is same as that of mean density of Earth. We have to calculate the radius of this planet. If the man can come out from the gravitational field of this planet by jumping. Okay, so we have to calculate velocity of the person, that is escape velocity of this planet. Now escape velocity of this planet v equal to root under 2gh, so 2 into g and h is the 1.5, so this is the root over 3g is the escape velocity. Now if we compare the escape velocity of this planet and Earth, so look at this. This is the v by ve, so this is the r dash into 8 by 3 pi g rho, this divided by r into root over 8 by 3 pi g rho. Mean density of this planet is same as mean density of the Earth, so this term cancel out. Okay, now here v equal to, look at this, root over 3 into g. Here v equal to root over 2g radius of it, so this is the r dash by r. Okay, now g cancel out, therefore look at this. This is the r dash into root 3r divided by root 2r. Okay, so this is the root under of 3 by 2 into r, so this is the root under of 3 by 2 into 6400 kilometer, so this is the 9600 kilometer. Now so this is the 40 root 6. Now root 6 is equal to almost 2.5 into 40, so this is the almost 100 kilometer is the radius of the planet. Okay, understood? Next, look at this, another problem. The Earth of mass 6 into 10 to the power 24 kg is compressed in such a way that it becomes a black hole. That is, the escape velocity from the Earth's surface is 3 into 10 to the power 8 meter per second. We have to calculate the radius of the Earth. Now look at this, the escape velocity ve, this is the root over of 2gm divided by r. So look at this, by squaring this we get ve square equal to, this is the 2gm divided by r. Now from this relation we have to calculate radius. So here from radius r is equal to, this is the 2gm divided by v square. Okay, so r equal to, 2 into this is the 6.67 into 10 to the power minus 11. Mass is this. So this is the 6 into 10 to the power 24. And this is the V square, that is 3 into 10 to the power 8 square. So this is the 9 into 10 to the power 16. So this is the 9 into 10 to the power 16. Look at this. This is the 10 to the power 16. This is the 10 to the power 11 minus 11 and 24. So this is the 8. So this and this is the 10 to the power minus 3. So this is the 2 into 6.67 into 6 divided by 9 into 10 to the power minus 3. Okay, 16, 8. Look at this, 16, 24, 8 into minus 11, that is the minus 3. Now look at this. This is the 2, this is the 3. Okay, now this is the 2.22. So look at this. This is the 4, this is the 4, so this is almost 8 point, look at this, 2 to 4, so this is the 8.88 into 10 to the power minus 3 meter is the radius of the earth. Now this is almost equals to 0.9 into 10 to the power minus 2 meter is the radius of the planet. Okay, understood? Next, now Kepler's law. Every planet, look at this, every planet revolves in an elliptical path keeping sun at one of its foci. So look at this, here planet revolves around this path and sun is one of its foci. Okay, the second law. The radius vector joining sun to planet swept out equal area in equal interval of time. Suppose a planet moved from position P to Q, so area swept by the radius vector is this. If area of swept be delta A in time delta t, then delta A by delta t, this equal to constant. Okay, when the planet is closer to the sun, then it moves from P dash to Q dash. Okay, so area of swept out is this by the radius vector. So this area equal to this area if time delta t is same. So look at this, if this area is equal to this area, then time interval to move from this to this is same as time interval to move from this to this. So closer the sun, the velocity of the planet is more. Now look at this, if r be the radius, this is the angle delta theta. So look at this is the perpendicular, so this is the r delta theta. So area swept delta A is the half base is the r into altitude is the r delta theta. Okay, so look at this is the half r square delta theta. Now delta A by delta t, this equals to half r square delta theta by delta t. Now delta theta by delta t is equal to omega. So this is the omega. So this is the half r square omega. Now r omega equal to v. So look at this is the r into v. Now mvr divided by 2m, that is L by 2m. So look at this, if delta A by delta t is constant, then angular momentum by 2m is also constant. Therefore angular momentum also constant. Therefore for a planet, the angular momentum with respect to sun is constant. So look at this, as angular momentum constant, so look at this, if this is the velocity v1, this is the r1, here look at this is the velocity v2 and this is the r2, so v1 r1 equal to v2 r2. So far away from the sun, velocity less, closer to the sun, velocity more. Okay, understood? You have to remember three things from the Kepler's second law. First of all, look at this, aerial velocity is constant. Okay. Number two, angular momentum is conserved. And number three, closer the sun, velocity more. Far away from the sun, velocity less. That is V inversely proportional to distance from the sun. Okay, understood? Now a numerical. The ratio between angular momentum and mass of earth is 4.4 into 10 to the power 15 meters square per second. Now we have to calculate the area described by the radius vector from sun to earth in a year. Look at this. Suppose this is the elliptical path of the earth. Now we have to calculate this area. Okay. Look at this. We know that aerial velocity, area by time, this equal to L by 2m. Look at this. Here L by m given. T known. T is the 365 days. That is this second. So look at this. A equal to, this is the half into L by m into T. Look at this. This is the half into 4.4 into 10 to the power 15 into T. T is the 365 into 86400 meter square is the area described by the orbit of the earth. Okay, this is almost 7 into 10 to the power 22 meter square is the area of this portion. Okay, next. Now Kepler's third law. The square of period of revolution of a planet is directly proportional to the cube of mean distance between sun and the planet. That is, if t be the period of revolution and r be the mean distance, then square of the period of revolution is directly proportional to the cube of the mean distance between sun and the planet. Look at this. That is T2 by T1 equals to R2 by R1 to the power 3 by 2. Okay. If we consider the circular path of the planet, look at this. This is the position of the sun and this is the position of the planet. Planet revolves with velocity v in its orbit of radius r. Now centripetal force acting on the planet, this is the gravitational force of attraction. This equal to g mass of the sun, mass of the planet divided by r square. Now this is equal to mv square by r. So look at this. This is the mv square by r, where v is the orbital velocity of the planet. Now from this condition, v equals to root under of g capital M by r is the orbital velocity of the planet. Okay, understood? Now total path of the orbit is 2 pi r. Period of revolution capital T. So look at this. Velocity v equal to total path divided by time taken. Okay. Now if we put this value here, so this is the 2 pi r divided by t. This equal to root under gm by r. Okay. Now squaring this, we get, look at this. This is the 4 pi square r square by t square equal to g capital M divided by r. So look at this, t square equal to 4 pi square divided by gm into r cube. Okay, that is t square proportionate r cube. Understood? Next, we know gravitational force F proportionate to 1 by r square. Then period of revolution t proportionate r to the power, this is the, and period of revolution r to the power 3 by 2, that is t proportionate r to the power 2 plus 1 by 2. If F proportionate 1 by r to the power n. Okay, here n equal to 2. Then look at this, T proportionate r to the power n plus 1 divided by 2. Okay, understood? Next, if gravitational force F proportionate 1 by r to the power 5 by 2, then square of period of revolution is directly proportional to x. We have to calculate x. From Kepler's third law, we know F proportionate, if F proportionate r to the power n, then T square proportionate r to the power, this is the n plus 1. Okay, now look at this, here n plus 1 is equal to x. So here n plus 1 equal to x and n equal to, this is the 5 by 2. So 5 by 2 plus 1 is equal to x. Therefore x equal to, this is the 7 by 2. Okay, understood? Look at this, two stars revolves in a circular path. Look at this, two stars revolves in a circular path of radius r. Look at this, this is the circular path of radius r. Due to their mutual gravitational force of attraction, look at this, if this is a position of one star, this must be position of the other star, that is the diametrically opposite point, such that the mutual force of attraction between them provides necessary centripetal force. Look at this is the force of attraction and this is the orbital velocity. So this force must be equal to, this is the mv square, this force must be equal to mv square divided by capital R. Okay, look at this, force of attraction along this direction, here velocity along this direction, so centrifugal force mv square, so centrifugal force mv square by R is directed along this direction. Now we have to calculate the mutual gravitational force of attraction. Look at this, this is R, so this obviously 2R. So gravitational force of attraction F equal to, this is the G, mass of one star, mass of other star, divided by square of their distance. Distance is 2R, so this is the 2R whole square. Okay, so look at this, this equal to this. Therefore this is the G m square by 4r square equal to m v square divided by r. Now this and this cancel out, this and this cancel out, therefore v equal to root under of gm divided by 4r is the velocity of each star. Okay, next. Now look at this, for mass m revolves in a circular path such that they form a square, that is distance between this and this, this and this, this and this and this and this are identical. We have to calculate the orbital velocity. Now look at this, suppose orbital velocity of this mass is the v. Now the centrifugal force acting on it, this is the mv square by a radius of it. Here radius is capital R. Okay, now the centripetal force is the mutual, now the centripetal force provided by the gravitational force of attraction between this and this, between this and this and between this and this. Now look at this, this is the radius R, so this is the diameter 2R. Now 2R is the diagonal, so side becomes, this is the 2R by root 2, that is root 2R. Now force on this by this is the G m square divided by 2R square. Okay, now this is the also same force, this is the F, this also F. Now what is the force of attraction? This, look at this distance is root 2 times more. Now this distance is 2R, this is the root 2R, so this is the root 2 times more than this. So gravitational force of attraction is inversely proportional to square of the distance. So 1 by root 2 square, that is 2, that is 1 by 2. So here force of attraction becomes F by 2. Look at this. If this is the F, this angle 45 degree, so this also F cos 45 degree. This is the this also 45 degree, this also F cos 45 degree. So look at this, the total force, this plus this plus this. Therefore look at this, 2F cos 45 degree plus F by 2. This is the centripetal force and this must be equal to mv square divided by r. Okay, understood? Now we know the value of F. Look at this, this is the F by 2 plus this is the root 2F, this is the mv square by r. So look at this, here F is the G capital M square by 2r square into 1 plus 2 root 2 divided by 2. This equal to mv square by r. Okay, now this m cancel out. Look at this, this is the r square, so this and this cancel out. Therefore v becomes, look at this, therefore from here v becomes, look at this, this is the root under of G capital M 1 plus 2 root 2 divided by 4. Okay, understood? Next, now artificial satellite. Human made satellite is called artificial satellite. Look at this, suppose this is the earth. A satellite revolves around the earth at an altitude h from the earth's surface. This is the radius of the earth. Now look at this, orbital velocity of the satellite be small v. So centrifugal force, this equal to m v square divided by distance from the center. So this is the r plus h is the centrifugal force. Now what is the force of attraction? Now force of attraction G into mass of the earth, mass of the satellite divided by square of distance between this. So this is the G capital M small m divided by r plus h whole square. Okay, now this force is equal to this force. Therefore this is the G capital M small m divided by r plus h whole square. This equal to, this is the m v square by r plus h. Okay, so v equal to, look at this, this is the root under of this and this cancel out. So this is the gm by r plus h. Look at this, here orbital velocity is independent of mass of the satellite. Now we have to calculate period of revolution. Look at this, the period of revolution is the total path divided by velocity. Now total path is the 2 pi into r plus h, this is the circumference. Okay, and velocity, this is the v. Now we know the orbital velocity. So look at this, here 2 pi, this is the r plus h into root under of, this is the gm divided by r plus h. Therefore t square equal to 4 pi square into r plus h whole square divided by gm divided by r plus h. Okay, therefore t square equal to 4 pi square, this is the r plus h whole cube whole divided by gm. Okay, now we have to calculate maximum orbital velocity and minimum period of revolution. Okay, now the orbital velocity of a satellite at an altitude h from the earth's surface is v equal to root under gm by r plus h. Now the velocity becomes maximum if the satellite is closer to the earth's surface. When h is less than r, that is the satellite revolves very close to the earth's surface, then look at this, r plus h almost equal to r, then V max, this equals to root under of gm divided by r. Now we know g equal to, this is the gm by r square. So look at this, gm equal to gr square. So from here you can write, this is the gr square divided by r. So this is the root under gr is the maximum velocity of the satellite. Look at this, if we put the value here, g is the 10 and r is the 6400 kilometer, it should be converted into meter. So this is the 8000 meter per second is the maximum orbital velocity of the satellite. Okay, understood? Now period of revolution t is equal to 4 pi square r plus h whole cube whole divided by gm. The period of revolution becomes minimum when orbital velocity is maximum. That is, the satellite is very close to the earth's surface. That is, here r plus h is almost equal to r. So here t equal to, this is the 4 pi square into r cube whole divided by g into mass of the earth. Okay, now we know g equal to, look at this, we know g equal to gm divided by r square. So gm equal to gr square. So look at this, this is the 4 pi square into r cube whole divided by, this is the gr square. Therefore look at this, this is the 2 pi root under of r by g. Okay, now if we put the value of r, radius of the earth, and acceleration due to gravity, we get, look at this, this is the 2 pi and this is the 6400 into 1000 divided by 10. So look at it, this and this cancel out. So 2 pi into, look at this, this is the 800, this is the 1600 pi second. Okay, it is almost equal to 1.4 hour. Therefore minimum period of revolution of a satellite is 1.4 hour or 84 minutes. Okay, so time period of a satellite must be greater than 84 minutes. Okay, now we have to establish the relation between period of revolution of a satellite and mean density of earth. We know mass of the earth is 4/3 pi capital R cube into mean density of the earth. If we put this value here, we can get T equal to, this is the 4 pi square into R cube whole divided by 4 pi R cube whole divided by 3 into rho. Look at this, R cube cancel out, pi cancel out. So look at this, 4 cancel out. So this becomes 3 pi by g rho. Okay, therefore T proportionate, look at this, T proportionate 1 by root over g. So period of revolution is period of revolution of a satellite is inversely proportional to the square root of mean density of the earth. Okay, understood? Please like and comment on the video. Okay, look at this, a satellite is at altitude 3400 kilometer. We have to calculate the orbital velocity of the satellite. Look at this, the orbital velocity of the satellite v equals to, this is the g capital M divided by r plus h. We know small g is equal to, this is the gm by r square. So gm is replaced by gr square. So this is the gr square divided by r plus h. So from here v equal to r into root over g by r plus h. Okay, now r is the 6400 kilometer. It should be converted into meter. G is the 9.8. Okay, and look at this, r h is the 3400 kilometer, r is the 6400 kilometer. Now r plus h, that is this plus this, is equal to 9800 kilometer. It should be converted into meter. So look at this, this is the 9800 into 10 to the power 3. So look at this, this is the 6400 into 10 to the power 3, and this is the 9.8, and this is the 9.8 into 10 to the power 6. This and this cancel out. So this is the 6400 into 10 to the power 3 whole divided by 10 to the power 3. This equals to 6400. This is the meter per second. So 6.4 kilometer per second is the orbital velocity of the satellite. Okay, next. Now a small satellite is revolved very close to a planet of mean density 10 gram per cc. G is 6.68 into 10 to the power minus 8 CGS unit. We have to calculate the period of revolution. We know the period of revolution t, this is equal to, this is the 3 pi by g into rho. So look at this, this is the 3 pi, g is the 6.68 into 10 to the power minus 8 into rho is the 10. This is almost equal to 3755 second. Okay, so this is the 1.04 hour is the period of revolution of the satellite. Okay, now we have to establish the relation between potential energy, kinetic energy and mechanical energy of a satellite. Look at this, a satellite of mass m revolves around the earth at an altitude h from it. Radius of the earth is capital R. So orbital velocity v is equal to root under of gm divided by r plus h, where m is the mass of the earth. So its kinetic energy ek, this equal to half m v square. Now v square is equal to gm by r plus h. So look at this, this is the half m gm divided by r plus h. So look at this, this is the ek, this equals to g capital M small m divided by 2 into r plus h. Okay, understood? Now potential energy. The potential energy at an altitude h from the earth's surface, this is the EP equal to minus g mass of the earth, mass of the satellite divided by distance from the center of the earth. Look at this, this is the r and this is the h. So distance from the center of the earth is r plus h. So mechanical energy E is equal to, this is the ek plus EP. So look at this, this is the G capital M small m whole divided by 2 into r plus h minus G capital M small m divided by r plus h. So look at this, this is the minus G capital M small m by 2 into r plus h. Okay, now this equal to this. So look at this, this is the minus ek. So mechanical energy, that is total energy, is the negative sign of kinetic energy. And look at this, this equal to half of this. So this is the half of potential energy EP. Okay, understood? Next, look at these two satellites A and B is at an altitude r and 3r from the earth's surface. We have to calculate ratio of their potential energy and ratio of their kinetic energy. Now you know the potential energy of the satellite EP is the minus G capital M small m divided by R plus H. So here EP inversely proportional to 1 by R plus H. Same way the kinetic energy EK, this equals to G capital M small m by 2 into R plus H. So kinetic energy also proportional to, this is the 1 by R plus H. Look at this. This is the EPA by EPB, that is potential energy of A divided by potential energy of B. Look at this. This is the inversely proportional to R plus H. So this is the, look at this. This is the R plus R and this is the R plus 3R. So look at this. This is the 4 by 2. This is the 2 by 1. Okay. Now this ratio is same as that of kinetic energy EKA divided by EKB, because both potential energy and kinetic energy inversely proportional to R plus H. So ratio of potential energy of A and B is same as ratio of kinetic energy of A and B. This is the 2 by 1. Okay. Now the radius of a satellite of mass m is 2r. Now it's transferred to another orbit of radius 4r. We have to calculate the work done. As satellite revolves around the earth, so it has both kinetic energy as well as potential energy. So the work done is equal to change of mechanical energy delta M, that is E2 minus E1. Now look at this. What is the final energy? Now the final energy is the minus G, mass of the earth, mass of the satellite divided by 2 into 4r. Now what is the initial energy? This is the G, mass of the earth, mass of the satellite divided by 2 into 2r. Okay. So look at this. This is the G capital M small m divided by 4r minus G capital M small m divided by 8r. So look at this. This is the G capital M small m divided by 8r. So G capital M small m by 8r is the work done or energy required to shift from 2r to 4r. Okay, understood? Next. Now what will be the increase of potential energy? Now look at this. The increase of potential energy delta U, this is the U2 minus U1. So look at this. This is the minus G capital M small m. This is the 4r minus this is the G capital M small m divided by 2r. So look at this. This is the G capital M small m divided by 4r. Okay, understood? Next. We have to establish the relation between orbital velocity of a satellite and escape velocity at that place. Look at this. We know the orbital velocity of a satellite at an altitude h. This is the gm divided by r plus h. Now escape velocity at an altitude h, ve equal to, look at this. This is the 2 into gm divided by r plus h. So look at this. ve by vo. Look at this. This is the root under of 2 gm divided by r plus h. Look at this. This is the root over gm divided by r plus h. So this is the root 2. Therefore v escape equals to root 2 into 2 vo. Therefore if the orbital velocity increases to root 2 times of the present value, then the satellite escape from its orbit. Okay, look at this. Suppose this is a satellite. It revolves around the earth with velocity v0. If its velocity increases to root 2 v0, then it escapes away from its orbit. Okay, understood? Now root 2 means 1.414 v0. that is 141.4% of V naught. That is, if the velocity of the satellite is increased by 141.4 minus 100%, that is 41.4%, then it escapes away from its orbit. Okay. Now condition to launch a satellite. Suppose a satellite launched with velocity v. Look at this. If v less than orbital velocity, that is v equals to root under gm divided by r plus a, then the satellite again reaches the earth's surface in a parabolic path. Okay. Look at this. If v equal to v naught, then the satellite revolves in a circular path. Then the satellite revolves in a circular path of height 8. Now look at this. If v greater than v naught but less than root 2 v naught, that is velocity of the satellite greater than orbital velocity but less than escape velocity, then the path of the satellite becomes ellipse. It has more velocity, so it revolves in an elliptical path. Okay, and its time period more than the time period at this point. When v greater than equal to root 2 v naught, then the body escape away from the earth's gravity. Okay, now energy needed to launch a satellite. Look at this. The energy needed to launch a satellite, delta W, this is the final energy minus initial energy. Now final energy means the mechanical energy. So mechanical energy at the altitude h, this is the g capital M small m divided by 2 into r plus h. Now initial energy, look at this, the satellite is at rest on the earth's surface. So initial energy is only potential energy. So look at this, this is the potential energy at the earth. So this is the gmm by r. Okay, now look at this, here g capital M small m whole divided by, this is the 1 by r minus 1 by 2 into r plus h. Okay, now there is a numerical. Now what is the minimum energy required to launch a satellite of mass small m at an altitude toward around a planet of mass capital M? Look at this, the energy required delta W, this equals to, look at this, this is the g capital M small m, this is the 1 by r minus 1 by 2 into, this is the r, h is the 2r, so this is the 2r. Okay, now look at this, this is the g capital M small m whole divided by r, this is the 1 minus 1 by 6. So look at this, this is the 5 by 6, so energy required 5 g capital M small m divided by 6r. Okay, understood? Next, now look at this, geostationary satellite and polar satellite. First of all, geostationary satellite, the satellite which revolves from west to east in 24 hours on the equatorial plane of the earth is called geostationary satellite. The altitude of the satellite is 3600 km, and as its period of revolution is 24 hours, so it's always stationary with respect to a point on the earth. And velocity of the geostationary satellite is 3.12, this is the kilometer per second. Okay, now polar satellite, the satellite whose orbit is normal to the equator is called polar satellite. Its height almost 720 km and period of revolution is 102 minutes, and in its every revolution it passes through North Pole and South Pole. Okay, what is used? The polar satellite is used in weather forecasting, GPS system, and to form a map of a place. Now, the use of geostationary satellite. The geostationary satellite is used for telecommunication and live telecasting. Okay. Now, weightlessness in a satellite. When a satellite revolves around the Earth's gravity is balanced by the centrifugal force experienced by the satellite. So, net force acting on the satellite is 0. So, any person in the satellite becomes weightless because Earth's gravity is balanced by centrifugal force due to rotation of the satellite. Okay. Now a numerical. A geostationary satellite is at altitude of 6 hours from the Earth's surface and its period of revolution is 24 hours. We have to calculate the period of another satellite which is at altitude of 2.5 hours. Okay. Now look at this. Here T square proportionate R cube. Look at this. R1 that is orbital radius of geostationary satellite. This is the 6R plus R. So this is the 7R. And period of revolution T1, this is the 24 hour. Now we have to calculate the period of another satellite which has orbital radius. This is the 2.5R plus R. That is 3.5R. So this is the 3.5R. Okay. Now T2 square by T1 square. This equal to, look at this. This is the R2 by R1 whole cube. So look at this. This is the 3.5R. Okay. And this is the 7R whole cube. So look at this. This is the 1 by 8. Therefore T2 by T1. This equals to 1 by 2 root 2, that is 2 root 2. Therefore T2 equals to 24 by 2 root 2, that is 6 root 2. Therefore period of this satellite is 6.2 hour. Okay. Next. Now an important numerical. Two satellites S1 and S2 have period of revolution 1 hour and 8 hours. We have to calculate the radius of the, look at this, the radius of the first satellite is 10 to the power 4 kilometer. Now we have to calculate the radius of second, and we have to calculate the linear velocity of second. We also calculate the linear velocity and angular velocity of second with respect to first. Okay. Now look at this. Here T2 by T1 whole square, this equal to, this is the R2 by R1 whole cube. Now look at this. Here T2 is the 8 hour, T1 is the 1 hour. So look at this. This is the 8 by 1 whole square. This is the R2 by R1 whole cube. So look at this. R2 by R1. This is the third root of 64. Therefore this is the 4. Therefore R2 equal to 4 R1. Now R1 is equal to 10 to the power 4. Therefore, so the radius of S2 is 4 into 10 to the power 4 kilometer. Okay, understood? Now velocity of first V1. Look at this. The velocity of first V1. This is the 2 pi R1 by T1. So look at this. This is a 2 pi into 10 to the power 4 by 1. This is the kilometer per hour. Now velocity of second. Look at this. 2 pi. This is the R2 by T2. So look at this. 2 pi into 4 into 10 to the power 4 divided by 8. So this is the pi into 10 to the power 4 kilometer per hour. Now we have to calculate the velocity of S2 with respect to second, that is V2 minus V1. So look at this, here V2 minus V1. So look at this minus this. So this is the minus pi into 10 to the power 4 kilometer per hour. Okay, now relative angular velocity of S2 with respect to S1. So this is the V2 minus V1 by R2 minus R1. Look at this, R2 is the 4 into 10 to the power 4 kilometer, R1 is the 10 to the power 4 kilometer. So R2 minus R1 is 3 into 10 to the power 4 kilometer. Now angular velocity, this is the V2 minus V1 divided by R2 minus R1. Look at this is the minus pi into 10 to the power 4 divided by, look at this is the 3 into 10 to the power 4. This and this cancel out. So this is the minus pi by 3. This is the radian per hour. Is the angular velocity, is the relative angular velocity of second with respect to first. Okay, many thanks for watching this video. This video will be extremely beneficial for you for your class 11 main, NEET and advanced. Please like, comment and share the video. Okay, thank you.